The final presenter in the session will be Professor Immo Kleinschmidt, who is at the London School of Hygiene and Tropical Medicine. His main research interest is malaria epidemiology, and he's recently relocated to Windhoek in Namibia, where he's also working with the Southern African Development Community Elimination Aid Initiative.
Thank you. So I will be talking a little bit about the study design and why we had to choose this design and what implications that might have. And then on the overall results, putting them together from all 5 countries, although I should point out that we don't have final data for incidence cohorts from India yet, so there's still a piece that is missing from that. As Tessa has already pointed out in the introduction, vector control has been a huge success story over the past 15 years, and the large number of cases that have been averted due to malaria control since 2001, nearly 80% of those are estimated to be attributable to the use of insecticidal products, and therefore the loss of susceptibility obviously could signal a catastrophic rebound in disease. And this was, of course, observed in a real-life situation. I think a slide that many of you are familiar with in KwaZulu-Natal in South Africa, when there was a switch from DDT to pyrethroid, and unbeknown to the malaria control program, there was pyrethroid resistance in phonestis, and that resulted in a 10-fold increase in malaria cases, almost 10-fold increase, which was then brought back under control by switching back to DDT, to which phonestis was fully susceptible at that time. So that obviously a case of real concern and real impact that resistance can have, in this case, on IRS. A couple of more recent studies, I think, that are important to contextualize the results of this 5-country study, is a study published last year by Lindblad et al. From Malawi, which showed that L-Alliance still had a 30% effectiveness, even in an area of high resistance to pyrethroids. Another study published earlier this year showed that exposing resistant mosquitoes to sublethal doses of pyrethroids can interfere with parasite development in mosquitoes, and therefore could enable treated nets to prevent malaria transmission despite increasing vector resistance. A further study by Viana et al., which showed that delayed mortality effects occurred in highly resistant malaria vectors following exposure to insecticide on L-Alliance, and because delayed, not captured through the standard tests. A study by Churcher et al., which has been widely presented, but to my knowledge not published yet, using models based on bioassay and experimental HUT data, predicted that even at low levels of resistance, there would be an increase in incidence due to loss of personal protection, but at higher levels of resistance, this would be far more substantial due to the loss of personal protection as well as community protection of the nets. So that is just a few pointers from the literature. The study design that was adopted for this study, the considerations for that were that we needed something that was common across all countries. There was as much standardization as was possible to achieve in the methods and the outcomes. And of course, importantly, there was a need for adequate statistical power, and hence to replicate in as many sites as possible. And as was said previously, we had over 340 sites in those 5 countries where we could make these measurements. But an important thing to be aware of is that this is an observational study, since we cannot randomly allocate resistance, and therefore a caveat that goes with all observational studies, that it provides weaker evidence and it is never free from confounders. The epidemiological endpoints had already been mentioned, and the effectiveness of nets could only be measured by comparing incidence or prevalence in users with the incidence in non-users, who were of course not randomly allocated but were simply people who didn't comply with net use, and hence this is only a measure of personal protection, but again to note that this is not from a randomized allocation. So just to briefly point out how this was done, in each of these 340 places a cohort of children was recruited, and they were tested regularly for infection and or disease. Data on net use collected at each visit, and at the same time in those same places larvae were collected in breeding sites, raised to adults, and then tested for susceptibility using the standard WHO test. And the idea was that we would have from these many locations a measure of resistance or susceptibility and a measure of malaria, either incidence or prevalence, and one would imagine that if there was some association, that you would get possibly more malaria when you have lower levels of susceptibility. I'll expand this in the following slide a little bit. So that was essentially one hypothesis, is that we would have lower levels of malaria morbidity measured by one of those 3 indicators, where we had higher levels of mosquito mortality measured in bioassays. The second hypothesis, to do with the use of nets, was that if we compare users against non-users, that the ratio of incidence or prevalence in users to non-users should be a number less than 1. If the nets if users and non-users have exactly the same incidence, then of course we would have a ratio of 1, and it would indicate 0 protection. The higher the effectiveness of the nets, the lower that ratio would be. And again, the hypothesis being that we might see something like, these are purely hypothetical data, that we might see something like this, where we would have higher effectiveness, where we have higher susceptibility to the nets. And this, of course, we also did by dichotomizing the clusters into those with higher and lower resistance based on the median as the best measure of discriminating between the different levels of resistance from the data. Just a quick word about the methods that were used. Were essentially generalized linear models, and in all estimates, adjustment was made for within cluster correlation of responses, and for the analysis for multi-country results, meta-regression was used to show the effect of nets overall. So the 3 sets of results I'll be summarizing here are the time trend in bioassay mortality, the impact of resistance on the effectiveness of LLINs as far as personal protection is concerned, the impact on the effectiveness of IRS, and any association between insecticide resistance and any of those measures of malaria morbidity. Just a word about the use of the WHO test. In this study, we required a maximum number of sites or clusters, 340 as mentioned before, with resistance characterization. And this was to some extent at the expense of more intensive measurements at each location, And this is the reason why we went for the standard bioassay test, because it is there was no problem in doing this at many locations, not just once, but for each year of the study. So we have over 1,000 data points. But overall, so that really precluded using other methods that would have given us, at this level, intensity measures of resistance. Overall, nearly 80,000 specimens were tested this way, so a large exercise, really. So here are 5 of these graphs are what you've seen in the country presentations, except India, that hadn't, beg your pardon, that hadn't been shown before, showing the trend in bioassay mortality over the years of the study, and then the 6th graph is all those data combined. And on the face of it, it looks like there hasn't really been a trend, it's just an up and down. But that is largely confounded by differences in countries, particularly India, which came in late into the study and where susceptibility or mortality was still very high. So if we adjust those results for country, we get a significant trend of just under 5% per annum on average in decrease in bioassay mortality over time. So a steady increase in resistance, although uneven, as was pointed out from the country presentations. So a significant trend in phenotypic resistance over time on average. So effectiveness of nets. If we look particularly, and I'll just highlight results from one country before going to the multi-country results. Combining the 3 years, which Charles had already presented in individual years for case incidence in Kenya, we see that nets significantly protected users, because we had in both the lower resistance and in the higher resistance stratum, and particularly in the higher resistance stratum, a lower incidence of malaria amongst users compared to non-users, and that was a significant difference both in the low and high resistance stratum between users and non-users. And this difference in effectiveness, as measured by the rate ratio, was not significantly different. So no interaction between resistance and effectiveness of nets. So these data then show the protective effect of L-alliance in both higher and low resistance clusters. If we look at the results for all countries combined, here shown by a forest plot, there are obviously ups and downs, but most of the estimates of the effect of of the effect of nets comparing users with non-users are on the side below 1 for an odds ratio here, because this is from all the prevalence surveys that were conducted throughout the study period in the various countries, and here including India, which was not shown in previous results, giving us an overall effect estimate of 0.68 as an odds ratio for the protective effect of nets between users and non-users. Although there are individual differences, really no evidence of heterogeneity here between those survey results. The top 3 are from the high transmission countries and the bottom from the low transmission countries. If we split these data by higher and lower resistance, again now using a median for all these countries combined, which of course gives uneven numbers for individual countries in terms of lower or higher resistance, here is the prevalence of infection comparing users with non-users in the higher resistance clusters, those were those classified as having median bioassay mortalities of less than 73. So again, we see an overall effect. Of course, this is on somewhat smaller data sets. And India is very low prevalence, so there were no cases in the stratum with higher resistance, and that is why it doesn't appear in this slide. But again, we see an overall estimate combining all this of an odds ratio of 0.69 in the higher resistance clusters globally. Looking at the same in the lower resistance clusters, a very similar estimate of 0.68. But of course, there is heterogeneity, and we didn't see any impact in Sudan, which is one of the two low transmission countries, but we did see an impact in India. And here, there's perhaps some question about whether one should combine the lower and higher transmission, but I'll show you the same for looking at incidence. But before that, just to summarize the above three slides, we see an overall impact here of nets looking at users versus non-users with this odds ratio of 0.68. And no evidence of any difference between the higher and lower resistance places as classified by the bioassay median. For historical comparison, just a reminder here from the Cochrane review, we had an odds ratio of 0.87, which was a 13% protective efficacy. So it is of a similar order of magnitude, but I think we need to be clear here that the Cochrane data were based on randomized trials and hence free of confounders, which, of course, our observational study cannot claim. Looking at case incidence, again combining all countries except India, because those data are not in yet, we again see here for the higher transmission countries a protective effect of 0.56. The low transmission countries, this is only Sudan now where we don't see an effect. In fact, there's probably considerable confounding there. It looks like people using nets had higher incidence than those not using nets, and that could well be explained, but we can't adjust for that in the data by people using nets in places where biting pressure is higher. Anecdotally, that's certainly confirmed, is that people often use nets even before they go to sleep because of intense biting pressure, and hence there could be a higher usage of nets in places where there's more malaria, but that is just speculative. Overall, we see a rate ratio of 0.73, but with quite significant heterogeneity between the higher transmission and lower transmission areas, and perhaps some question about, therefore, whether we should combine this estimate from low transmission with that of high transmission. Dichotomizing again between higher resistance and lower resistance, we see pretty much the same kind of effects. So we see a strong effect amongst the high transmission country combined, but no effect in the lower transmission. Again, this excludes India, where we did see a strong effect in prevalence, but we don't yet know what it will be for incidence. And overall, a marginally significant effect if we combine those two. Looking at the lower resistance, where median mortalities were above 73, a similar picture. And if we compare the data from the last slide, the higher resistance with those of this slide, there was no significant interaction between the effects in lower resistance and higher resistance areas, as shown by this p-value here of 0.426. Again, for historical comparison, from the Cochrane review, the rate ratio from randomized trials was about 0.5, a 50% protection, which is similar to what we see in the higher transmission countries, again with the caveat that this is not from randomized trials, whereas the Cochrane review data were. Then briefly, association between resistance and malaria morbidity, and there are a lot of data here, so I'll only present one slide which kind of represents all of them. This is if we combine all sites over all years for which we have data and plot the bioassay mortality against, in this case incidence. On the left-hand side, just the raw data as we have them. On the right-hand side, because there's a large difference between incidence in the low and high transmission, and that's why you see a lot of dots or crosses that look like they are just along the zero line. If we standardize for country, then they're spread out more and we see the same sort of thing. But if one tries to fit a regression lines through there, it is essentially horizontal. So there's no trend in terms of higher mortalities and case incidence. And if we analyze that, we get no effect really across those sites. For all locations combined, no evidence of an increase in case incidence associated with pyrethroid resistance based on this measure. And we have a similar data set for prevalence, again a large data set, and I could show you a similar plot, but essentially the same result, that we see no trend between, or no association between bioassay mortalities in those 340 locations over the 5 years and prevalence of infection as measured in the surveys. So lastly, just briefly, and this has really been shown before, so I can just show it very quickly. The one place where we could look at the effect of resistance on IRS was the one study area of Galabat with the 26 clusters that were randomized. And this is quite strong evidence because here we have a randomly allocated control group of clusters, which were the 13 clusters which had L-lines only, and where we could see this big difference when we switched to an effective insecticide compared to one to which there were high levels of resistance, which was in the year 2012 when deltamethrin was sprayed, showing something similar, perhaps not in the same magnitude, but the same kind of thing that we saw in that introductory slide of what happened to IRS in South Africa, of course, where there was no second level of protection through nets, where the only vector control was IRS. So, conclusions. And we need to be aware that these are observational data, hence they are subject to a degree of confounding, but they are from a very large data set, and we see similar trends across those countries, with some exceptions, of course. So first of all, insecticide resistance was highly variable between years and was heterogeneous on a relatively fine scale. And there was a significant trend of increasing pyrethroid resistance in the main malaria vector species across that period of time, with a very large number of insects tested in many locations. Secondly, there was no evidence of an association between malaria disease burden and pyrethroid resistance across all those locations. Thirdly, there was evidence that L-lines provided personal protection against malaria in areas with pyrethroid resistance, and there was no difference that we could detect in L-line effectiveness between higher and lower pyrethroid resistance places. Fourthly, there was evidence from one area in Sudan that with high L-line coverage, that IRS with an insecticide to which there's resistance provided no additional protection, whereas the switch to an insecticide to which there was susceptibility halved malaria incidence relative to the control arm of LLINs, showing the impact of resistance on IRS. And lastly, again, this was only from one site where we had data on this. The development of pyrethroid resistance was slower in areas with L-alliance plus a non-pyrethroid IRS, in this case bendiacarb, in the Galabat area, than in an area with L-alliance only, sort of confirming the message that it is possible to slow the development of resistance through the right use of insecticides. So those are our 5 main conclusions, and again, I can't go through all the organizations and individuals because it's a very large number of people who've contributed to this. The funding, of course, from the Bill and Melinda Gates Foundation, and both malaria control programs and research institutions in the 5 countries, and my colleagues at the Liverpool School and the London School contributed, obviously, to all this work in a major way. Thank you very much.